Any questions before we get started? So today we're going to continue on with our radical reactions. We'll talk a little bit more about stereochemistry, number of products, all that stuff, and then we'll learn two new types of reactions with radicals. And then towards the end of the lecture, now that we have a halogen in the molecule, we'll talk about a different type of substitution. So remember, radicals are CH substitution. So a hydrogen is being substituted for a halogen. Then the next type of substitution we're going to learn is that halogen can become any of the other functional groups that we've learned already. And that's a different type of mechanism. So we were talking about taking 2-methylbutane and then we said there was 1, 2, 3, 4, minimum of 4 unique sets, but 5 because of those prochiral hydrogens on carbon 3. And so if we substituted at carbon 3, we can get those stereoisomers, those enantiomers. And this question is asking you, what is the R to S ratio of the 3-chloro-2-methylbutane? So it's going to be 1 to 1. And so again, why is that? Now, keep in mind for this problem, I'm just showing you the substitution at C3. So what happens there? But because chlorine is pretty reactive, it can substitute anywhere. So when one of those hydrogens gets abstracted, we end up with that radical. So that's one way of representing it. Another way of representing it, sort of in 3-dimensional space, would be with the p orbital. And so I put the electron in there. And that can abstract from the top face or the bottom face. And so if it does that equally, what that sigma bond right there represents, because that's a chiral center, it's a mixture of both enantiomers. So here's our mirror plane. And so we would get a 1-to-1 mixture of those. And so we use that term prochiral to describe those type of hydrogens, because when you do substitute them, they become different products. So here's one of them, and the question is asking you, what is the name? You said A. I don't think so. Anyone have a different guess? B. I do think it's B. So the first thing, let's get the numbering of the chain. So we're going to number it this way. So that's the chain length, and we're numbering it that way because chloro comes before methyl. So substituents are named alphabetically, and then we're going to give the chlorine the lowest number. So 2-chloro, 3-methyl. So let me draw in the H, and then in blue we'll assign priorities to the 4 different substituents. So carbon 2 is the chiral carbon. Chlorine would be priority 1. Hydrogen would be priority 4. And we're using the atomic numbers to assign those. And then we end up with this issue of carbon and carbon. So since they're both the same atomic number, we have to look at the substituents bonded to them. This has 3 hydrogens. This has 2 carbons and a hydrogen. So that's going to win. That'll be priority 2. So if that's 2, that's 3. And when you make your circle, you're going clockwise, but the lowest priority group is pointed out towards you. So you have to flip from R to S. So that's how we get the S designation. So again, priority of the 4 groups is based on atomic number. The higher the atomic number, the greater the priority. And then when you're doing your clockwise or counterclockwise, you always want the lowest priority group pointed away from you. So in this case, because it's pointed towards us, we just reverse the direction. So here's, again, we'll ignore sort of the response, but something to think about. So again, I used to do these with eye clickers, and then students would punch in a number. So it says how many monochlorinated isomers, constitutional and stereo, would be produced when methyl cyclopentane is the starting material. So we'll use methyl cyclopentane, chlorine, and light. And it's asking us how many total products, including all constitutional and stereo. So the first thing we'll do in blue here, let's determine the unique sets of hydrogen. And as we do that, we'll classify. So we have a methyl group, that's primary. Then we'll just go down the chain. We have a tertiary. So tertiary is called methine, just a CH. And then the molecule has symmetry. So we start here, we walk to that carbon, then we walk out either way. And so those secondaries are now equivalent. And then we walk further along and we can see that those secondaries are equivalent. So we have 1, 2, 3, 4 unique sets. So to a first approximation, you could say there would be 4. But then once you start drawing them, then you have to look for stereoisomers. So let's draw sort of the 4 where we substitute a CH for Cl, and then we'll ask the question about stereoisomers. So let me organize this a little bit. I'll say primary, tertiary, secondary, and then we'll draw the products. So when we look at that, does that generate a stereo center? So the answer is no, because the carbon has 2 hydrogens bonded to it. So we'll just keep a tally here and say that's one product. Now we'll look at the secondary, or the tertiary CH. We'll substitute that. So we ask the question, is that a stereo center? So the answer is no, because when you march off from that carbon to either of the carbon substituents in the ring, they're basically mirrored. So this part of the molecule, that mirrors that mirrors that. So that's not a stereo center. So this just gives 1. And then for the next, either of these secondaries, we're just going to substitute an H for Cl. So now, did we generate a stereo center? So we did. But look at the molecule a little closer. How many stereo centers does it have? So it ends up having 2. So that's a stereo center. And now that methyl group also turns into a stereo center. So we have 2 to the 2, that equals 4. So that carbon now, if you look at it, so this one where the methyl is, you have methyl, then H. Then when you go along, you run into that other secondary. But now the one that was substituted with chlorine, it's now different. So that makes that carbon has 4 different substituents now. And then we can do the other secondary on the ring. So this carbon here, where we substituted for chlorine, is that a stereo center? It is. So what you have to be careful of, when you march out, you see CH2, CH2. You would say, well, that's the same substituent. However, it's not, because you have to consider the entire path. So even though those CH2s are the same, when you go out one further, it's then different. So that ends up being a stereo center. And then it also makes this other carbon bearing the methyl group a stereo center as well, for the same reason. So here we end up with 2 to the 2 equals 4. So total we have 1 plus 1 plus 4 plus 4. That gets us 10. I think that's right. So beware a confident man. You know, that's where the term con man comes from. So I'm 99% certain that's right. Give myself 1% is I'm backed into a corner. So any questions on that? So I don't think I have this as a slide coming up, but say in a separate instance, we use the same starting material, but now we switch to bromine. Remember, the difference between chlorine and bromine is that bromine is more selective. So at what class of hydrogen, primary, secondary, or tertiary, will the bromine substitute? So at the tertiary. So bromine's going to primarily just give you that as the major product. And so we would classify that as now a tertiary bromide. So just like we classify hydrogens, we can classify halogens. And if you're able to do that, that's what the ionic mechanisms are based on that we'll learn at the end of the lecture. You have some haloalkane, you classify it, and then that will tell you what type of mechanism can happen with that. So this compound is 1-chloro-1-methyl-cyclopentane. And the question asks, is it a meso compound? Do you remember what the definition of meso is? So number one, it has to have at least one stereocenter. And number two, it has to have an internal mirror plane. So this molecule does have an internal mirror plane, so like right here, but it does not have a stereocenter. So the answer for this would be no. So the way it's drawn looks a little weird. You're slicing that chlorine. Imagine chlorine as a ball. You're slicing that ball in half. So remember, because the carbon's sp3, it's tetrahedral. You have like the methyl group here, and then the chlorine down here, and it's like sliced in half. So 1/2 of the chlorine atom mirrors the other half. So to practice our nomenclature, which of the following is 1R, 2R, 1-chloro, 2-methyl-cyclopentane? So in terms of the name, just so I can ask some more questions. So that would be the numbering on the ring. So the 1-chloro, 2-methyl. So we want the 1 position to be R. And so when we're drawing the bond from the carbon to the chlorine, should it be the bolded wedge or the dashed to give us the R? I heard a dash. The wedge. So I think it's the wedge is going to give us the R. So we can eliminate B and C. And then for the 2 position to be R, should that be the wedge or the dash? Dash. I don't think so. So I think the answer is A. So let's walk through it and assign the priorities. So for the 1 position, we'll use the blue numbers, and then the 2 we'll use green. So chlorine will be the highest priority. Let's draw that hydrogen in. That's going to be the lowest priority. Then we're going out to carbon and carbon. This carbon right here is more substituted. So wait, we want 1, 1. If that's 2, that's counterclockwise, right? So 1, 2, then 3. So that would be S. So you think it's C? Okay. So based on that, 1, 1, 2, 3. Counterclockwise S. 1, 2, 3. So if that's forward, 2, 3. Yeah, so that would be, this would be S. And so that would be R. Does that make sense? Does everyone buy that?
Could you go over that again?
So let me start fresh. Unfortunately, this app doesn't allow me to erase things. Like, I have the eraser on, but can you see that dot? So there's a dot appearing on my screen, but it's not allowing me to erase anything. Oh, there it is. I can erase some stuff, but not. I'm trying to erase that line over B. All right, anyway. So Cl, H, H. So we're at position 1. Chlorine's highest priority. Hydrogen's 4. And then the issue was carbon and carbon. So this carbon has an H, a carbon, and a carbon. This carbon has 2 H's and a carbon. So that one has to get priority 2. So 2 and then 3. Because the lowest priority is going back, we end up going this way. So that's counterclockwise. So that makes that S. So therefore, the bond to that chlorine has to be the dash. So the dash was the correct answer. So we're actually going to eliminate A and D. And so now we have to figure out what the methyl group is. So a squiggle is basically we're determining is it going to be a wedge or a dash. Maybe let's just how do I want to do this? Let's just focus on response B. We'll assign the priorities, see what it is, and then see if it's right. So we'll put in the hydrogen. So that hydrogen's coming out towards us. Now this one we have carbon, carbon, and carbon. So then we have to look at the three things bonded to those. So the methyl group has H, H, and H. So the atomic numbers for those are 1. So 1, 1, and 1. This one has 2 hydrogens and then a carbon. So 6, 1, and 1. This has a hydrogen, a chlorine, and a carbon. So that carbon has to be the highest priority because of the chlorine. So that's going to be 1. The hydrogen is the lowest, so 4. Then of the 2 remaining carbons, that one's more substituted. So we get 2 and then 3. So overall, this is going clockwise. So we would initially assign it as R, but since the lowest priority group is facing us, it would switch to S. So that means that C has to be the correct answer.
So why would for B, why would why would it be the opposite, like the 2 and 3 of like priority?
You're asking about these numbers 2 and 3.
Yes.
So although I kind of verbally explained it, let me just write some numbers down. So that the methyl group has 3 hydrogens. So let's just write 1, 1, and 1. So if you add those, you would get 3 in terms of just a number. Now this other one, you have hydrogen, so that's a 1. Another hydrogen, that's a 1. And then the carbon is atomic number 6. So total, that would get you 8. So that's another way to differentiate when you have the same element. So because that hydrogen's pointed towards you, that stereo center is flipped, so that becomes the S. And so that means the methyl group has to be the wedge. And so we do end up with C is the correct answer. So I mean, there's a little trick you can do for this, when you have 4 possibilities. So 2 stereo centers gives rise to 4 stereoisomers. If you just do the analysis like for one response, then you can figure out, does the bond need to be a wedge or a dash? And then you can do eliminations that way. So it says, what is the relationship between 1R, 2R, 1-chloro, 2-methylcyclopentane, and 1R, 2S, 1-chloro, 2-methylcyclopentane? So the substituents, their locations are all the same, right? What we're looking at are basically those, the CIP stereochemical designations. We can see that the 1R is the same, and then 2R, 2S changes. So that makes them diastereomers. If each position was exactly opposite, then they would be enantiomers. So now pay attention to the nomenclature for this. What do you think? These are different compounds. So what we can see from the locations, 1R, 2R, and then 1R, 3R. So enantiomers, again, the stereochemical designations are exactly opposite. For diastereomers, one of them is different. The reason that these are different compounds is because of that, essentially the methyl group ends up in a different position. So those are not diastereomers. Is that clear? So again, and if in terms of like the name, it would be easy to identify if things were identical because the name would be the same. But if you were given the structure and the structure was like rotated somehow, they could still be identical. And then what you have to do for that is just look at the stereoisomers, figure out R and S, and then are they the exact same? So just based on the words of the name, it's pretty easy to figure out. Identical, if you're given a structure, always just figure out the R or S designations. Any questions? So that was CH substitution using molecular chlorine, Cl2, or molecular bromine, Br2. Now what we're going to do is look at another type of CH substitution using a different reagent. So as we move forward now in this module and then module 5, it's important to know the functional group names, what elements constitute those functional groups, and then we're going to start learning a lot of these reagents. So, one way you can do this is just make these index cards with the reagent name, the structure, and then what functional group it's acting on. Because sometimes you'll have a reagent that can act on different functional groups, but you have to diagnose the conditions to determine which one it's acting on. So this reaction name is called allylic bromination, and then the reagent we're going to use is abbreviated NBS. So this structure right here, down at the bottom, that's NBS. That stands for N, so nitrogen bromosuccinimide. The key part of this reagent is that nitrogen bromine bond. So that's a fairly weak bond. So nitrogen and bromine are both heteroatoms. So if we put in the lone pairs, we know heteroatoms have lone pairs. Nitrogen has 1, bromine 3. There's an electronic repulsion of those lone pairs, and essentially that makes the bond weaker, so it's easier to cleave. So the allylic position, as a reminder, there's our alkene, our carbon-carbon double bond. We know that those two carbons are sp2 hybridized. The allylic position is an sp3 hybridized carbon right next door. And so we saw that those are the easiest type of CH bonds to cleave. So we can cleave that through homolysis. And again, that generates an allylic carbon radical and then hydrogen. So what NBS is going to do is specifically target allylic hydrogens. And throughout the rest of the semester, I'll, mention some properties of these things. So NBS is a white solid. It's a source of bromine radical. Molecular bromine, Br2, is a liquid. And if you ever had the opportunity to hold a bottle of it, say you had a bottle of it like this size, it's really dense, so it's heavy. And the other thing is when you open it, it fumes. It smells like really strong public swimming pool, like that chlorine smell, but it's a little more intense. So in that fuming that you see it's not good for you. So it's a difficult reagent to handle. So these alternative reagents like NBS exist because it's a solid. It doesn't have the same toxic properties as Br2 does. In general, solids are easier to manipulate, weigh out, and measure. So we're going to use that reagent and look at molecules specifically with allylic CH groups. So let's consider, here's the numbering of the chain. So at the 2 position, there's a methyl group. At the 1 position is the start of an alkene. That's 4 carbons long. So 2-methyl-1-butene. I'll highlight in blue. So blue equals sp2 hybridized carbons. So how many allylic carbons does this molecule have? So it has 2, and I'll highlight those in green. And so we have 2 allylic carbons. So without even teaching you the mechanism or going any further, if I tell you that NBS specifically substitutes CH of allylic carbons, how many substitution products would this generate? So a good response, good first approximation would be 2. So let's just draw those out and talk about them. So we've just identified what the allylic carbons are. We see we have a methyl group, CH3, and a methylene, CH2. And we've substituted H for Br. So we came to this first approximation of 2 different structures. Then we asked the question, so let me just say this was from a primary substitution from a methyl, and then this was from secondary. Of the primary substituted product, does that generate a stereo center? So the answer is no. So that's 1 product. What about substitution of the secondary? Is that a stereo center? So that generates a stereo center. So we actually get 2. So that's equivalent to, you have the bromine coming out, and then the bromine going away. So that's our now sort of second approximation. So 3 total. But actually there's more. And so we'll understand the thing that gives the allylic radical the stability, why it's so easy to cleave. There's a resonance form that's going to impact the total number of products we can get from this. So we've identified these. Let me again highlight them again in green. So green was sp3 allylic carbons, and then we further classified that as a primary and then a secondary. So we have primary allylic and secondary allylic. So the question says, recall that allylic radicals are stabilized by resonance. How many distinct allylic resonance hybrids are there? And so we'll answer that on this question, on this slide here. So we said that was HA and that was HB. And all I'm going to do, I'm not going to show you how it gets abstracted. I'm just going to show you the radical, and then we'll look at the resonance forms. So from HA, it generates that radical. And then a resonance form would be that. So again, resonance forms, they're not two separate, distinct things. It's just telling you, indicating to you, guiding you, where is the radical density. Of these three carbons, 1, 2, and 3, the radical density really is at 1 and 3. So let's do the same analysis for HB. So again, 1, 2, 3. The arrows? So this electron, single electron moves. Then from the pi bond, one of those electrons is going to come over. So those two electrons meet, that forms the pi bond. Then the other electron of the pi bond hops over to the end. So notice what happened though in that second resonance form. We now have this alkene that has these different substituents. So there's actually another resonance form that looks like this. In this one, the radical is on the same side as a hydrogen. In this one, the radical is on the same side as the methyl group. But again, it's still showing you the radical density is on those 1 and 3 positions. So this is the type of analysis that you use to determine the total number of substitution products. Because from our first approximation, we were just saying, hey, there's the radical, we're substituting from that. Or there's the radical, we're substituting from that. But now you have these resonance forms that you can substitute from, and they'll put the bromine at those positions. So overall, how many different, total different? So 1, 2, 3, 4, 5. We can draw 5. When you look at the path from cleaving the C to HA in those two resonance hybrids, like if you draw the product of substituting, so now we're just going to draw wherever the radical is, we're then going to draw that bond to bromine. So when you look at those two things, are they different? Are they the same? You said they're different? They might look different, but they are the same. The only thing that makes them appear different, remember in the prior module we talked about sigma bond rotation? So if you rotate around this bond right here, you'll get that compound. So that's the same compound. So for these resonance forms, they're producing the same thing. We saw from this one that you can produce two stereoisomers, the R and the S. For this one, when you substitute, you're not going to generate a stereocenter, but it's different from the other products we've already formed. And then when we do the same thing for the last one, notice now from those two radicals, the compounds are different. So in this alkene, the methyl groups are on the same side. In this alkene, they're on different sides, so they are different compounds. So the total number of compounds that this can produce is 1, 2, 3, 4, 5. So even though we started from 2 allylic carbons, the methyl and the methylene, from the allylic resonance, we see that the substitution can take place either at the 1 or the 3 carbons of that system. And then we ask the question about, does it generate a stereocenter that can lead to more possible products? So we initially came up with 5 resonance forms, but in reality, there's only 4 unique ones because that one leads to the same product. So which one will lead to a stereogenic center? We said that was B, because when we substitute, that's the one that gets 4 unique substituents. Any of those other ones, A, C, or D, the carbon atom is still having 2 hydrogens. So the total number of constitutional and stereoisomers we found to be 5. And so here they are drawn out for you. We won't spend time doing it now, but what you can do to practice is just make like a little table. So if we say, for each one, how many unique carbons does it have? How many unique sets of hydrogens and their ratios? That's a good way of practicing that exercise. And you'll see that You know, you'll get, some of them might be the same number of carbons, that sort of thing, but then when you do the hydrogen analysis, they'll be different. And so that's how you differentiate them. So there are the two stereoisomers from that secondary position. So what ratio are they formed in? So that's going to be 1:1. Again, because the radical exists in the p orbital with the top and the bottom face. So you get an equal amount, a 1:1 ratio. So let me ask another question. So say you were able to isolate these two from the rest of the other. You put it in the polarimeter and measure the optical rotation. What would that be?
0.
It's going to be 0. So when I look at this, just real quick, assigning priority, bromine would be 1, hydrogen 4. Then of our 2 carbons, that carbon, see how it's a double bond? We actually count that as 2 carbon substituents. So this would be, because we have carbon and carbon, the priority would be here, because when you go out, you add carbon, then you count that twice. So carbon, carbon, and carbon. So that's priority 2, that's priority 3. We're going clockwise, so that would be the R. And then we know, since that's the mirror image, that's the S. So in the polarimeter instrument, you make your sample up. It's 1:1, so one of them is going to rotate light one way, the other rotates it the exact opposite way, and those cancel out to 0. And so don't forget about, everything from a racemic mixture 1:1 to your pure enantiomer. You have those different ratios in there, what that enantiomeric excess number is telling you. Any questions? So the next reaction we're going to learn, this has a different name to it. So with molecular chlorine, molecular bromine, and NBS, those all did CH substitutions. The NBS was specific for allylic CHs. Under these conditions now, we're doing an addition. So things are not being substituted. So we're doing an addition to an alkene. So we know an alkene is a carbon-carbon double bond. And then what we're adding to it are the elements of HBr. So of that carbon-carbon double bond, one carbon gets an H, the other gets a bromine. So overall, the hybridization changes from sp2 to sp3 for both. And then you still have to ask the same questions. Am I generating a stereocenter? And then I have this funky word here, regiochemical. So what does that mean? Let me highlight maybe I'll just use red. Those are the 2 sp2 hybridized carbons of the alkene. So let me redraw the structure in black there. but now I'm going to color them different. So I'm going to say one is blue and the other is green. And the reason I did that is because this molecule is not symmetric. Those two carbon atoms are different. So the word regiochemistry is telling you that whatever you're adding to that double bond, you can add it in two ways. So for example, the HBr, the H could either go on the blue carbon or it could go on the green carbon. And then the same for the bromine. So this is what we're adding. We're adding HBr across that alkene. And then we're using this reagent here. So tert-butyl peroxide. A peroxide is an oxygen-oxygen sigma bond. So you've probably heard of like hydrogen peroxide. You might have that in your bathroom. You pour it on your scrape or your cut. It fizzes a little bit. So it's like an antiseptic. So tert-butyl peroxide is used for a very specific purpose in this reaction to generate radicals. As I said before, when you have, that type of bond, when it's heteroatom to a heteroatom, that's a weak bond. So it's pretty easy to cleave it homolytically. So overall, it's still a radical mechanism, but now we're going to use that tert-butyl peroxide to add the HBr to that alkene, but notice the two products formed. We say one is formed in the major amount, the other is formed in minor or trace or not formed. So if I put the colors back in, so I want that one to be green, and the other one to be blue. How can we explain why the major product is formed that way? So when I talked about, remember, classifying halogens, I would say that is a primary bromide, and then this is a secondary bromide. So we get 1-bromopropane as the major product. And then how would we know that? Again, we've done the exercise of uniqueness. So 1-bromopropane, the uniqueness set would be three unique type of carbon, 3 unique set of hydrogens, and then a ratio 3:2:2. So for the 2-bromopropane, we have 2 unique type of carbon, 2 unique sets of hydrogen, in a ratio of 6:1. So this is what I sort of meant when I've said this in prior lectures. You have one starting material, it can produce 2 possible products. And then we use the uniqueness stuff to differentiate them. Now, through the mechanism, that's how we'll understand why we get the major and why the other thing is not formed. But the uniqueness is just there to help us differentiate them. So from our bond association energy table, so homolytic bond association energies, that big table with all the functional groups and the energies, HBr requires plus 366 kilojoules per mole to cleave. So that homolytic cleavage compared to molecular bromine, which was plus 193. So Br2 is a lot easier to cleave. So if you start from 0, you hit 193 before you hit 366. So why would we even use HBr if it requires so much energy to cleave? Well, it turns out that HBr plus the peroxide allows the reaction to proceed under these radical conditions. So notice the bond dissociation energy of the tert-butyl peroxide. It's plus 157. So when that sigma bond cleaves, each oxygen gets a radical. And so we generate 2 of these alkoxy radicals. So that radical, it's higher in energy, it's hungry, it scans the scene, it sees the HBr. It's going to abstract that hydrogen. So the HBr bond cleaves, we form an OH bond, and then we form the bromine radical. So when we compare those energies to break the HBr, we said it was plus 366. When we make the OH bond, that releases negative 440. And so overall, when you add those 2 numbers together, you see it's exothermic by negative 74 kilojoules per mole. So that's a favorable process. And so now what that bromine radical is going to do, it's going to add to the alkene. So this is, again, this is different from the other mechanisms. It's not abstracting an H now, it's adding to the alkene. So that's where we have our choice. I think I was using green for this, and then blue for that. So you have 2 pathways. That point at which the pathway splits is called a bifurcation. Notice I have one going up and one going down. So we're gonna think of the pathway that's going down as the favorable one because it's lower in energy. We want to form a bond between the bromine radical and then the blue carbon, so carbon A. So the way we do that, the single electron moves, then of the pi bond, 1 electron comes out. So that forms the carbon-bromine bond. The other electron has to end up on carbon B. Now, if we classify that radical, what type is it? What class? So this is a secondary radical. If we did the same sort of arrow pushing the other way, but now we're going to add that bromine to the green carbon. The radical ends up on the blue carbon. And then what class of radical is that? Primary. Remember when we were learning about CH bond cleavage in terms of what's the easiest thing to break? It was tertiary, then secondary, then primary. So that's the order of stability. So it's more favorable to form a secondary radical than it is a primary. So the secondary radical is lower in energy. That's going to then move forward to abstract a hydrogen from the HBr. So we have this single electron coming out, an electron from the HBr bond, and then the other one forming the bromine radical. So that's your chain, that bromine radical. So when we do that, we end up with the HBr adding that way, then plus our bromine radical. So now when we classified that as a primary bromide, right? So one way to think about these conditions under this mechanism is that you're always going to get the lesser substituted bromide as the major product. Because remember, the HBr can add two ways. Just draw out both ways. Classify the bromides. And then whichever one is the lesser class, that's going to be the major, because it comes from the more substituted carbon radical. So I know that's a lot to keep track of, but again, however you want to learn these things, if it's index cards or however, there's ways you can sort of minimize your mental burden of predicting the major product. So we said when it adds to A, that generates a secondary radical. When it adds to B, that generated the primary radical. And then again, from our CH bond cleavage, the radical stability trend was tertiary greater than secondary greater than primary. So really what we're comparing now is that secondary versus that primary. So we know that that's more stable. It's going to be formed preferentially. Then it goes on to react with the HBr. And then this was our propagating radical. Any questions? So the addition of the bromine radical to propene by HBr and tert-butyl peroxide, which of the following proton NMRs belongs to the major product? So the answer is A. And again, the way, as we said before, in terms of the uniqueness set, there were 3 unique carbon, 3 sets of hydrogen, and then their ratios. So what we're looking at is the signals here are your sets. So that number was 3. We count 1, 2, 3. That's the sets. For the bottom one, there's only 1, 2 sets. So we don't even have to look at like the multiplicity, that n+1 rule, because those numbers 3 and 2 are different. if in some other reaction they ended up being the same unique sets of hydrogen, then you have to go into, those ratios, then the multiplicity to differentiate them somehow. So let's see if we understand that in the last couple minutes here. So here we have methyl cyclopentene, and we're treating it under those conditions with HBr and tert butyl peroxide. And it says, what is the name of the major product? So B. So how can we look at the alkene to determine that? So remember, you have these 2 carbons of the alkene. And you have to envision the bromine adding to the one that's going to generate the more stable radical. Let's just draw them both out, then classify them. That'll help us determine the name. So if the bromine adds to the blue carbon, it generates that radical. If it adds to the green carbon, it generates that radical. So what class is this radical? So that's tertiary. And then the other one is secondary. So we know that that's going to go on to the major product. And so when that tertiary radical abstracts a hydrogen, you get your product. And then we just number around the chain, and we would find that 1-bromo 2-methyl cyclopentane is the major product. So we're about out of time. We'll have some more questions on this specific substrate that sort of reviews all the concepts. And then now that we know how to make these different haloalkanes, we'll classify them, and then we'll start learning about ionic mechanisms.